All right, we're recording. Okay, I decided that the exam will be up to what I will do today. Okay, the exam. You have 8 hours, you have enough to study. So, up to what I do today, the exam will be on. Um, any questions?
Is it all going to be computation, or should we like any proofs or?
No, just mostly computations.
All right.
Yeah. Should be similar what you have been doing on the homework and so forth. Okay. Uh, okay, really quiet it down, I guess. All right. Um, it's dark here, so I have the light on. And we're going to continue recall if you have a sequence an, then az is n equals 0 to infinity an z minus n for z bigger some number rho. This is the definition of the z transform of the sequence an. Okay. And we have been doing some computation, and what we're gonna do is this is a theorem 3.36, and this is a factorial. You remember the factorial sequence, right? Like we did whatever x to the r or something. Okay. So this is the factorial function. Ouch. We are talking about. All right. So suppose z of an is az, and az is there. Then 1 z of, and this is n plus k minus 1 to power k an equal minus 1 to power k z to power k dk a over dzk of z. And if an equal 1, then n plus k minus 1 to power k is z factorial zk over z minus 1 k plus 1. Okay? So let's do the proof. Start with 1, and let's start with the definition. So let's take a look at dka over dzk of z. That is dk over dzk of n equals 0 to infinity. Okay. Of n equals 0 I'm looking at something here. Is k minus 1 over k minus 1. That will be n an z minus n. So I differentiated once. Okay. And so this is gonna be for k equal 1. This is going to be minus 1 to power k, n equals 0 to infinity, n plus 1, n plus 2, n plus k minus 1, an z of minus n minus k. Okay? You differentiate this one z times, k times. All right. And if you keep writing this, this is minus 1 to the k, z minus k, n equals 0 to infinity. And this factor is gonna be n plus k minus 1 to power k. This is the factorial function. An z minus n. So this here is nothing but this one. This is the factorial function. And then this is the result. And then you will get minus 1 to the k, z minus k, z multiply, then multiply by, I'm looking for za, and then write this as minus 1 to the k, z minus k, this one, that is this one, and then divide by z to the k, and then you will get it. Okay? Again, this one here, this one is this one. Okay? So what you need to do is divide both sides by minus 1 to the k, z minus k, and you will get this one. Okay? You will get that one. All right. So for part 2 is really simple. So you have an is 1. So you have z of n plus k minus 1 to power k is, by this theorem, minus 1 to the k, z to the k, dk over dzk of, what is the z transform? What is az? Az is z over z minus 1. Because az is z over z minus 1. And the derivative of that, the case derivative of that is this one. You get the z factorial over all that. Okay? And then you have a minus n plus, so they will cancel out. All right. Any questions? Okay, there's a next theorem called This is theorem 3.3.7. This is called the initial value theorem. Okay, initial value theorem. All right. So then we're gonna let AZ is the Z transform of AN. And this is for Z bigger than rho. Then 1 A0 is the limit as Z approaches infinity AZ. 2 A1 equal to the limit as Z approaches infinity ZAZ minus A0. Excuse me. 3 A2 is the limit as Z goes to infinity. Z of AZ minus A0 minus A1 over Z and so forth. Okay? Now, assume, remember the proof of 1, the series converge. So what is the limit as Z goes to infinity of AZ? That is, okay, the limit as Z goes to infinity n equals 0 to infinity AN Z minus N. But at n equals 0, there is no Z. So this is A0 plus n equals 0 to infinity, the limit as Z goes to infinity of AN Z minus N. Now remember, the series converge. So as Z goes to infinity, this series is finite, and as Z goes to infinity, this is gonna be 0. Okay? So what I'm saying is, this is A0 plus n equals 0 to infinity, AN times the limit as Z goes to infinity, Z minus N. Okay? And this is 1 over Z to power N. So as Z goes to infinity, this goes to 0. So this is go A0 plus 0, which is A0. So that shows, that proves 1, not that proves this one. Okay? Any questions? For 2 is the same. 2 is the same. For B, so AZ is n equals 0 to infinity AN Z minus N, and that is A0 plus A1 over Z. Okay? Plus n equal to 2 to infinity a n z minus n. Okay? And then you take the limit, z goes to infinity of az, that is gonna be a0 plus a1 over z, okay? Uh, let me take it back for a second. Maybe I spoke too soon. Let's multiply by, so if I multiply z by both sides, multiply by z, so zaz equal za0 plus a1 plus n equal to 2 to infinity an z minus n plus 1. So we're multiply by z on both sides. And if I do that, now if I take, so this means is the lim as n goes to infinity of z of az minus a0. So I brought this over here and I factored the z out, equal to a1 plus n equal to 2 to infinity an the lim as z goes to infinity z minus n plus 1. Well, this goes to 0, so that is a1, and that proves the theorem. Okay, so part C is the same, and we're not gonna do it. Okay. And one more theorem I will do. Okay, we have other theorems I can prove, but and these theorems play some important role in a few things. Okay, so we have theorem 3.3.8, and it says if we have az is z of an, then the lim as n approaches infinity an is a lim as z approaches 1 of z minus 1 az. Okay. All right. So let's take a look at of z of an plus 1 minus z of a n. All right, so what is that? That is n equals 0 to infinity a n plus 1 minus a n z minus n. Well, we know what z of a n plus 1. What is that? So that is z of a z minus a 0 minus a z equal to, this is by corollary, this is by corollary 3.1, okay, is equal to n equals 0 to infinity a n plus 1 minus a n z to power minus n. Okay. So we're gonna, by the previous theorem, as n goes to infinity, okay, oh guys, I made a mistake here, typo. Not, the book is correct. This is supposed to be z goes to infinity, okay? All right. So this is supposed to be, so if I take the limit, of z goes to 1 of z a z minus a 0, okay, minus a z equal to, this is gonna be, if I'm gonna keep going on, this is gonna be of a1 minus a0 plus a2 minus a1 plus an plus 1 minus an and a plus. Keep going. I mean, sorry, up to here, because I'm doing the limit. Okay. And then okay, so this is the limit as z approaches 1. Of z minus 1 a z, and you see here, if you let z equal 1 here, you get a 0 minus, okay, a 0 equal to, you see all these cancel out, okay, is equal to minus a 0, all right, plus the lim as n goes to infinity of an plus 1. Okay. So this cancels with that. And then we will have, this is the same, but this is the same as n goes to infinity of an. And then we have the result. Okay. Because it doesn't matter, lim of an plus 1 or an as n goes to infinity is the same. All right. Any questions? Now we're gonna use this stuff to discover some few things. All right. So here's a couple examples. Example 3.6. So what is of an plus 1 if az is z squared plus z over z minus 1 cubed? So we want to find z of an plus 1 if az is equal to that. Okay. So by corollary 3.1, we have z of an plus 1 equals z az minus a0. Okay. So now if I know, so we need to find a0 and then we are done, because I know az, I can multiply it by z, but I don't know what a0. Okay, so by theorem 3.37, a0 is the limit as z goes to infinity of az, and that is the limit as z goes to infinity of z squared plus z over z minus 1 cubed, and that goes to 0. Hence, z of an plus 1 equal to zaz minus 0, that is zaz from here, and that is z cubed plus z squared over z minus 1 cubed. Okay. these people came spraying my lawn, and it's with a liquid, and it's raining. I don't know if it's gonna be effective or not. Oh, all right. Any questions? Now let's do another example. You see, we did this one. That was easy. Let's do another example. Let's say example 3.7. So we want to compute the ZAN plus 2, given that AZ equal to Z over Z minus 1 plus Z over Z minus 1 squared. Okay? Well, this is AN plus 2, so we need to use that corollary. All right? So again, by corollary 3.1, we know ZAN plus 2 equals Z squared AZ minus A0 minus A1 over Z. So if I already know this. So what do I need? I need to know this one, and I need to know this one. You see what happened? This is A0. So we need to know this one, and we need to know this one. Okay? Well, let's take a look at theorem 3.7. The one we just did a little bit ago. By theorem 3.37, we erased it. So we know by theorem 3.3.7, what do we have? We have A0 equal the limb as Z approaches infinity of AZ, and that is, where is AZ? AZ is this one, of Z over Z minus 1 plus Z over Z minus 1 squared. And that is 1 plus 0, that is 1. So we know A0 is 1, because the limit of Z over Z minus 1 as Z goes to infinity is 1. The limit of Z over Z minus 1 squared as Z goes to infinity, that is 0, because the denominator has a higher power, right? So we need now A1. I need A1 again. And A1, this is by the same corollary, sorry, by this one here. A1 is the limb as Z approaches infinity, Z of AZ minus A0 minus A0. This is A1. And that is the limb of Z approaches infinity, okay, of z times z over z minus 1 plus z over z minus 1 squared minus 1. So this is a little bit fishy, so let's take common denominator. Because if you don't take common denominator, you would assume this is infinity. You know what I mean? Because you have minus z. So let's take common denominator. And the common denominator is z minus 1 squared. That will be z times z minus 1 plus z minus z minus 1 squared. You see, I took a common denominator. Okay, so let us play it out. It's gonna be z of z squared minus z plus z, z squared minus z plus z, minus z squared plus 2z minus 1 over z minus 1 squared. Okay, so this go away, this go away. So we have the limit as z approaches infinity. We have 2z squared minus z over z minus 1 squared, and that is 2. Okay? All right, so now we know the answer. So all you have to do is, we know what A0 is. Okay? Yeah, we know A0 is 1. We know A1 is 2. So we can apply this one and find the answer. Okay? Now use the star. And this is the star. Okay? And we are done. All right. Let's take 5 minutes break. I need to go speak with these guys and I'll be right back. Okay? Miss Daddy, did you? Does the picture looks brighter to you today? Is there any improvement in the picture, or what do you know? What do you think? Nobody answers me.
What'd you say?
That the picture looks brighter?
No, it looks good.
Well, Lily has a lot of sway over the course, guys. Somebody asked, if Lily is a part of this course, how much sway does she have over it? Yeah. Hi, Lily. Come here. Lily, come. Oh, she's sleeping on the chair. She growl at the people spraying the yard, and then she lay on the couch. She's a lazy pup. What can I say? I wish I have her life. All right. Okay. So we did a couple examples related to the corollaries and these two theorems. So these two theorems are important in a sense. You don't find these theorems in a regular textbook. Okay? So they're my invention somehow. All right. Now I'm gonna give you some result because I'm really getting tired of going through all the proofs. I've been trying to do a lot of proofs for you, so you know how to carry them. But this one, the answer is, I mean, the proof is in the book. So for 0 less or equal to r less or equal to n, we have the z of the factorial function nr is 1 plus z minus 1 to power n. Okay, so they see the book for the proof. So what is the deal with the bookstore and the book now? What did you guys have to do? All right. So I thought the bookstore allowed you to have the book for like July something. What happened after that?
Yeah, we are supposed to pay for that, or we had an option to opt from there and then not paying anything. The date was 9th of July.
Okay. You know, I have no control over my book, okay? It's the publisher that does whatever they want. So I don't have much really to say in it. All right. Well, can you be honest with me? Can you print it out when they gave it to you, or download it?
There's no way to download the book, or like I think there are like options you can print certain pages, maybe 1, 2 pages, but you cannot print maybe like if you want to print 50 or 10 pages, you cannot do that.
Oh, okay. And what about downloading it?
There is no way to download the book.
I saw that there is a download link on the actual like Vital Source textbook. So yeah, like what Chris just said, it just has a watermark on each page.
Is it working? Did you try like downloading the book?
I don't know. I don't know. I did not write my books to become rich, so I just need to tell you that. I just wanted to share knowledge, okay? Anybody taking 535 on the fall? Oh, John is.
Yeah, I'm taking 535 fall.
Eh?
Yeah, I am taking 535.
You're gonna take 535?
I don't remember the course code, but I'm taking another course with you in next semester, so fall.
Yeah, okay. Well, Peyton, you don't need it because you're graduating, right?
Yeah, I was just curious.
It's 535, boundary value problem and PDE. I'm just writing a book for it with Taylor and Francis textbook, but the book will not be available when the semester starts. I just did the galley proof yesterday before it goes to the printer, but they're so slow. So, but I will share my digital copy with you, so you don't have to buy a textbook. All right. Now here's another theorem. The Z transform of 1 over n factorial is e to power 1 over z to the Z transform of 1 over n minus r factorial is z minus r e to the 1 over z. Okay? Think about this for a second. How would you do this? Write out the formula for 1 over the Z transform of 1 over n factorial. Go ahead and write it out. No. Well, we'll do the proof of 1 z of 1 over n factorial is n equals 0 to infinity 1 over n factorial z minus n. And that is n equals 0 to infinity z minus 1 to power n over n factorial, and that is e to the z minus 1, that is e to the 1 over z. Okay? And any questions? You see how simple it is? For 2, we're gonna make use of theorem 3.34 which says z of an minus k is z minus k of z of an. Okay? So if we take, so we let an equal 1 over n factorial, then an minus r is 1 over n minus r factorial. So r is k. So this one for this will be z minus r. If I use this, will be z minus r, zan is e to the 1 over z. Okay, there you go. And it's done. Okay. Any questions? All right, we're gonna do another theorem related to periodic function sequences. The theorem is kind of long. The proof. So this is theorem 3.3.11. Suppose the sequence an is a periodic of period t. That is the rate. That is an plus t equal an for all n. If z of an equal az, then see how loud she is? There, this is the formula. And I do have a nice proof for it. Okay? Really. All right. So there is a nice proof for this one on the. Do I have it with me? No. Okay. Lily? Here's Lily, she's angry. Let the guys do their job, okay? You're not gonna go outside and scare them off. I need them to do the law. You know? Okay? Yalla, bye. Go. Now go to the couch. I'm not done yet. All right. I really strongly suggest that you go over the proof that is in the book on page 100. Okay? So just go over the proof. Here's an example, a quick example. Let an equal -1 to the n. And this is for n equals 0, 1, 2, and so forth. Then clearly, an plus 2 equal to an. Okay? So that is an is a periodic of period 2, because the an for n equals 0, you get 1. For n equal 1, you get -1. For n equal to 2, you get 1. For n equal to 3, you get -1. For n equal to 4, 1. N equal to 5, -1. You see? So the spacing is 2. Okay? You see why it's a period 2? Because the sequence repeats itself every 2 units. So everybody came together, the guys spraying and the trash people coming. All right. So Lily, stop. And so let's apply the formula that is z squared over b squared -1 n equals 0 to 2 minus 1 minus 1 to the n z to the minus n. Okay? Really? Oh boy. All right, so this is equal to z squared over z squared minus 1 times n equals 0 will be -1 0 to power 0 to power 0 for n equal 1 plus -1 to power 1 z minus 1. That's it. So that is z squared over z squared minus 1. That will be 1 minus z minus 1. There you go. Okay? Any questions? All right. So that is the end of this section. Okay, let's push it a little bit more. Let's go 10 more minutes. Let's see where these guys are. No.
Oh.
All right, so this is section 3.4, convolution. And that is an important section. And I need to copy it too. All right. Definition, and this is definition 3.4.1. The convolution of two sequences UN and VN is defined as U star V is given by M equals 0 to N UM V N minus N. Okay? I'm taking my time to distinguish between the U and the V and the N and the M. Okay? For example, two to the N star 3 to the N is M equals 0 to N. Let's take this is U, this is V. Will be 2 to the N times 3 to power N minus N. Okay? Also, 1 star AN is M equals 0 to N AM. Okay? Because if you take, we take V to be 1 and U to be N. And that is equal to, if I take, if you like, AN, I took it to be EM. And if I take Vn minus M, that is A N minus M. Okay? They are the same. All right. Any questions? It didn't stop. Or should they left? All right. I think I'm gonna stop here for today. It's too much distraction, I'll tell you that. I'm gonna stop here. And I know my computer is not gonna go out of juice today because I have it connected to the power. So, oh, by the way, let me make an observation. I was just looking at your homework number 3 today, and I noticed, let's say you have r equals 0 to n minus 1 and 2 to the minus r. You know, you have a to power r is a to power r over a minus 1. But you see this one is r equals 0 to n minus 1, 1/2 to power r. So a, that is your a. So a is not 2. Okay? A is not 2. A is 1/2. All right? So be careful. Okay? Because it has to be to power r, not minus r. Okay, the guy came back, so I need to pay him. All right, I'm gonna stop here. Isaac, stay online. I may be distracted for 10 minutes, okay? 5-10 minutes. Okay, guys, I'm gonna end